Okay, so in the last video, we introduced the concept of the Standard Model, and we talked a little bit about the three basic fundamental particles, okay, leptons, quarks, and gauge bosons. Okay, and primarily in the last video, we focused on leptons, the different types of leptons, and the idea of the conservation laws, conservation of charge, and conservation of lepton number. Okay, so in this video, we're going to move our attention to the second type of fundamental particle, which is called a quark. Okay, now we have so far discovered 6 types or flavors of quark, and they have very interesting names. The 6 flavors of quarks are up, down, strange, charm, bottom, and top. And you can see this chart here that I've put up on the slide. This chart is provided to you in the IB Physics Data Booklet, and so you don't need to memorize the charge of each of these. The up, charm, and top quarks have a charge of 2/3. The down, strange, and bottom quarks have a charge of -1/3. Okay, so that's kind of a strange notion, the idea of fractional charge. And you might say, how is it possible for something to have a fractional charge? Well, it's not exactly, and in fact, isolated quarks don't exist, which is something we'll talk about later. But all 6 of these quarks have what's called a baryon number of 1/3. Okay, so we have the up, charm, top, down, strange, and bottom quark, and of course each of those has an antiparticle. Okay, and so an antiparticle, remember, is identical to a normal particle, except that all of the numbers associated with that particle are reversed. Okay, so just to give you an example, if an up quark has a charge of 2/3 and a baryon number of 1/3, then an anti-up, which you would write with a U with a line over it, would have a charge of -2/3 and a baryon number of -1/3. Okay, so we've got 6 quarks and 6 antiquarks. And I said this before, but quarks do not exist isolated in nature. Okay, you cannot find an up quark just out in the wild all by itself. Okay, so quarks actually come grouped together. And there's 2 primary ways that quarks come grouped together. Okay, so let's talk about hadrons. A particle that is composed of quarks is called a hadron. Okay, and there's 2 types of hadrons that we're mainly going to focus on. Okay, mesons and baryons. Okay, a meson is a particle which consists of 1 quark and 1 antiquark. And now what that means, by the way, is since all quarks have a baryon number of 1/3 and all antiquarks have a baryon number of -1/3, that means mesons have a baryon number of 0. Okay, you can also think of it as a meson is not a baryon and therefore has a baryon number of 0. You do not need to memorize any mesons because their composition will always be given to you on any IB exam question. Okay, so a meson is a combination of quarks consisting of 1 quark and 1 antiquark, not necessarily the same antiparticle. Okay, so I'm not necessarily talking about like an up and an anti-up, but I'm just talking about 1 quark and 1 antiquark in general. Okay, and I'll give you some examples of mesons later on, but again, you don't need to necessarily memorize any of those, although it would be useful if you recognize some of them as being mesons. Okay, a baryon is a hadron, meaning it's made of quarks, and a baryon is a particle which consists of 3 quarks. Okay, now by far the most common example of baryons are protons and neutrons. Okay, so protons and neutrons are not fundamental particles, they are made of smaller particles. Okay, specifically, as we'll see on the next slide, a proton actually consists of 2 up quarks and a down quark, and a neutron consists of 2 down quarks and an up quark. Okay, and just to show you that works out as far as charge goes, remember that the up quark has a charge of 2/3, and the down quark has a charge of -1/3, and so a proton, which is up, up, down, would have an overall charge of 2/3 plus 2/3 plus -1/3, which is 3/3, which is 1. Okay, and likewise, a neutron, which is down, down, up, 2 down quarks and an up quark, would have a charge of -1/3 plus negative 1/3 plus positive 2/3, which would give an overall charge of 0. Okay, you are responsible for knowing the quark composition of protons and neutrons. That is something the IB would expect you to know. Okay, besides that, you're not necessarily responsible for knowing the composition of other baryons besides the proton and neutron, but you definitely need to know those. Okay, so we have a little chart here kind of showing you, different ways of classifying particles. Obviously, we have the leptons that we talked about in the last video, the electron, muon, and tau, and their respective neutrinos. And then we have hadrons, consisting of quarks, and we have mesons and baryons. Okay, remember again, mesons are made of one quark and one antiquark, and baryons are made of 3 quarks. Okay, so pause there if you need to add this to your notes. Okay, and then this is just a visualization of the proton and neutron as far as quark composition goes. Okay, and again, you are responsible for knowing these quark compositions for the proton and neutron. Now, just to give you an example of, a meson, okay, and again, you're not responsible for knowing all the mesons that exist because there's so many of them, but one example might be what's called a kaon. A kaon consists of one down quark and one anti-strange quark, okay, which would give an overall charge of 0. Okay, it's not possible for a whole particle to have a fractional charge, and so these particles always have to exist in such a way that the overall charge is an integer. Okay, so you can't have like a meson where the overall charge is like a fraction. That's not possible. Okay, another example of a meson would be a d-meson, which consists of a down quark and an anti-up quark. Okay, and there's many more. You can see on this chart right here some other examples of baryons and mesons. Okay, the proton, the antiproton, the neutron, those are all baryons. Lambda, omega minus, those are other examples of baryons, and you can see their quark composition down here. And then over on this side, you can see some examples of mesons. And again, this is not every single baryon meson in existence. You can see right here it says there's about 120 types of baryons, and there's about 140 types of mesons. Okay, so this is just to give you an idea of what different hadrons might look like. Okay, the pion is a very commonly seen meson on the IB exam. So if you can recognize a pion as a meson, that would be helpful. Okay. Okay, so notice a pion is up and anti-down. There's actually, and this is a positive pion, there's also a negative pion. That would be anti-up, down. Okay, so we have talked about lots of different fundamental particles so far, and this just kind of summarizes the different particles we've seen so far, and their lepton numbers and their baryon numbers and all of that. Okay, now let's get back to conservation laws, because we've seen lots of problems with conservation laws. Okay, so here's the third type of conservation law that we're going to talk about. This is called conservation of baryon number. And basically that simply says that in any given reaction, the baryon number must be conserved on both sides. Now remember, each quark has a baryon number of 1/3. Okay, and more generally, every baryon has a baryon number of 1. Right, because a baryon number by definition consists of 3 quarks. Okay, and so 3 times 1/3 is 1. Okay, in addition, all strange quarks have what's called a strangeness number of -1. All anti-strange quarks have a strangeness number of +1. In most reactions, the strangeness number is also conserved. Now, I will talk about conservation of strangeness number later because it's not conserved in every single situation. So the first 3 conservation laws, charge, lepton number, and baryon number, are always true. This thing called strangeness is not always conserved, and we'll talk more about the situations where it's not conserved later. But again, you only have to worry about strangeness number when dealing with strange quarks. Okay, so a proton, which is up, down, that has no strange quark, has no strangeness number. All right, so let's look at some more examples of problems with conservation laws. Let's see if these reactions are feasible based off of what we know about conservation laws. Okay, so take a look at this first reaction. We have a negative pion basically combining with a proton and producing a neutron, a negative pion, and a positive pion. Okay, So let's see if this violates any conservation laws. Let's start with conservation of charge. Negative pion has a charge of -1, and a proton has a charge of +1. A neutron has a charge of 0. Negative pion has a charge of -1, and a positive pion has a charge of +1. Okay, so we have 0 on the left, and we have 0 on the right, and so conservation of charge is conserved. Now, that doesn't mean it's a feasible reaction. It just means that it doesn't violate conservation of charge. Okay, now, normally we'd check conservation of lepton number next, but there are no leptons anywhere in this equation because pions are mesons, protons and neutrons are baryons. All of these particles are hadrons, and so they're not leptons at all, so there is no lepton number to check. Okay, but let's take a look at baryon number. Okay, so a pion is a meson, which means it has a baryon number of 0. A proton is a baryon, right? It's up, up, down, and so that has a baryon number of 1. Okay, a neutron is also a baryon, baryon, and so it has a baryon number of 1. And then both of these pions have a baryon number of 0. Okay, none of these particles have a strange quark in them. Okay, you know for sure about protons and neutrons have no strange quarks, and pions don't have strange quarks. Okay, so this first reaction is feasible because it does not violate any conservation laws. Okay, so this first one is okay. The second one, on the other hand, okay, if we check charge, the charge is conserved, but when we go to check the baryon number, remember the proton is a baryon number, or is a baryon, so it has a baryon number of 1. But pions are both mesons, and so they have a baryon number of 0. Okay, and so you would say this reaction is not feasible, and then you would justify that by saying that it violates conservation of baryon number, and then you would write that up, write that out in a nicer way than that. Okay, but this reaction is not feasible because it violates conservation of baryon number. Okay, so pause there and look at that some more. Okay, so let's do a few more examples. Okay, so take a look at this reaction right here. Here we have a neutron and a proton combining to produce, okay, think for a second with this first particles on the right side, okay, a positive electron is the same as an anti-electron, which is the same as a positron. Okay, so we have an anti-electron right here, and then we have an anti-electron neutrino. Okay, now this actually has 2 issues with it. Okay, and the 2 issues are this, and I can spot them right away. Okay, so first of all, charge is conserved on both sides because this neutron has a charge of 0, proton has a charge of 1, positron has a charge of 1. This is an anti-electron neutrino that has a charge of 0, so conservation of charge is fine. Okay, but right away I see there's 2 baryons on the left side of this equation. There's no baryons on the right side of this equation. Okay, so this reaction is not possible because it violates conservation of baryon number. Okay, not only that, but you can say the same thing about lepton number, right? Because there's 0 leptons on the left-hand side, there's 2 anti-leptons on the right-hand side. Okay, so this reaction is double impossible because it violates conservation of lepton number and conservation of baryon number. Okay, so you would say this reaction is not possible because it violates those 2 conservation laws. Okay, and here you can see on this chart how the numbers don't match up on both sides. Okay, if you take a look at this slide right here, you can see other examples of how reactions are either feasible or not feasible based off of whether or not they violate conservation laws. Okay, so this top one is feasible. That looks kind of sort of similar to the one we just saw, but it's rearranged in a way where it's feasible. This bottom one down here is not feasible because even though overall lepton number is conserved, if you break it down by family, notice that we have a lepton number of 0 on the left. We have a lepton and an anti-lepton, or what should be an anti-lepton, over here, okay, this is actually, it looks like the little line for the antiparticle is actually missing for some reason. Okay, I don't know how that happened, but that should be an anti-muon neutrino. But even if the line was over it, remember lepton number has to be conserved by type. Okay, and so if this is an anti-muon neutrino, and again, it should have the little line over it to indicate it's an antiparticle. The line is right here for some reason. It didn't move over correctly when I was rearranging the slide. But again, lepton number is not conserved by type because remember that there's the electron lepton number, the muon lepton number, and the tau lepton number, and they all have to be conserved on both sides of an equation. Okay, now just really briefly to talk about strangeness number, remember that strange quarks have a strangeness number of 1, basically, and actually, let me go back and show you what's on the chart in the data booklet. Okay, so this is what it says in the data booklet. It says all quarks have a strangeness number of 0 except the strange quark, which has a strangeness number of -1. Sorry, it's -1. And so that means if you had a quark, let's say a baryon that was strange, then it would have a baryon number of 1 and a strangeness number of -3. And the reason that's important is because strangeness is this concept of something that is conserved in some situations but not all situations. Okay, so strangeness is not conserved in situations involving the weak interaction, the weak nuclear force. Okay, in situations where you have one quark changing into another type of quark, strangeness is not conserved. Okay, in other situations, strangeness is conserved, meaning it's the same on both sides of the equation. Okay, but in situations where one quark changes into another type of quark, strangeness is not conserved. Okay, the other 3 conservation laws are always true. Strangeness is only true in situations not involving these 2 things. Okay, so that's what I wanted to say about conservation of strangeness. Okay, besides that, I just want to look at a few more IB examples before I end this video. Okay, so these are all from past IB exams. So this question says, when a K- meson collides with a proton, the following reaction can take place. Okay, so here we have the K- meson. They tell you it's a meson, which means it has no baryon number. There's a proton it's colliding with, and it produces what they call a K0 particle, a K plus particle, and X. And then it says X is a particle whose quark structure is to be determined. The quark structure of mesons is given. And it says state and explain whether the original K- particle is a hadron, a lepton, or an exchange particle. Now this question is super easy as long as you understand basic terminology. The fact that it is a meson automatically means that it falls under the category of hadron, because a hadron is a particle consisting of quarks, or combinations of quarks. And remember, the 2 types of hadrons we've talked about are mesons and baryons. Okay, so to answer this question, you would just explain that a meson is a hadron because it consists of quarks, right? Specifically 1 quark and 1 antiquark. Okay, so this is one of those questions where definitions are important. Very easy to question to answer as long as you understand what a meson and hadron are. Okay, next question. Again, super easy question as long as you happen to know it, and that's just something you have to know. State the quark structure of the proton. All right, the quark structure of a proton is up, down. Okay, you just need to know that. That's something you need to memorize. Okay, that should be automatic. Okay, neutron is down, up. Or up, down. The order doesn't really matter. Okay. And then this question says the quark structure of particle X is SSS. Show that the reaction is consistent with the theory that hadrons are composed of quarks. And I did not write out this answer. It's not written in the best way, but basically what they're trying to show is that if you were to write out this reaction up here in terms of quarks, it would look like this. So K- is S, anti-up, a proton is up, up, down. K0 is down, anti-strange. K plus is up, anti-strange. And then X is given as S, S, S. Okay, so notice that we have one down on each side of the equation. We have on the left 2 ups and 1 anti-up. On the right we only have 1 up. And if you look at the strange particles, we have 1 strange on the left, 2 anti-strange, and 3 strange on the right. Okay, so in other words, the types of quarks are basically conserved. Okay, so this is consistent with the idea that hadrons are composed of these quarks, because when you look at the individual quarks themselves, they don't change type, at least not in this reaction. Okay, so the way the question is written is kind of confusing, but that's basically what it's getting at. Okay, and then just one more example. It says possible particle reactions are given below. They cannot take place because they violate one or more conservation laws. For each reaction, identify one conservation law that is violent. Okay, so see if you can figure this out on your own. Okay, and here's what the answer key says. Okay, so hopefully now you should have a better idea of quarks, of hadrons, of mesons and baryons, and applying the conservation laws in more situations. So you should now be able to do all the conservation law problems on your topic 7.3 worksheet. Okay, so remember that there's 3 types of fundamental particles. There's leptons, there's quarks, and there's gauge bosons. Okay, we'll talk a little bit more about quarks in the next video, and then we'll talk more about gauge bosons, which have to do with the 4 fundamental forces that we've talked about before. And then we'll kind of wrap up talking about the standard model and try to see how all the pieces of that fit together. Okay, so as always, please let me know if you have any questions, and I will see you guys in the next video.